Okay, so now that we understand where the high pressure and low pressure areas are on the globe on a big scale, we can start to finish our picture of why the winds blow in the directions they do. So if we know that winds blow from high to low, we can start adding arrows on our globe to show wind direction. So winds tend to blow towards the equator because they are blowing from the high pressure at the 30 degrees north and 30 degrees south towards the equator. So from high to low, from high to low. Um, Farther away from the equator, we get winds blowing from the 30 up to the 60 from high to low, and opposite in the southern hemisphere from high to low. And once again, up at the poles, from high pressure to low pressure, from high pressure to low pressure. Okay, that's great. So let's see how that helps us with our initial question here of why the storms move the way they do. So let's add in our wind direction arrows. Let's use this color. Okay, so near the equator, winds are blowing from high to low, high to low, high to low, high to low. So this is, I've set these arrows up exactly the way we did on the last diagram. Problem is, these don't answer our question. We want to understand why the storms are moving from east to west near the equator and from west to east in the mid-latitudes. And we clearly have not answered that question yet. And that's why we've learned about the Coriolis effect. So that's the issue here. We need to bring in our understanding of the Coriolis effect, because winds, as they're traveling up above the surface of the spherical Earth, they trace a curved path on the ground. So now when we're drawing our arrows, they still go from high to low. So I'm going to start here at the 30-degree north line, and I'm going to draw my arrow towards the low pressure. But in the northern hemisphere, I know that winds curve to the right. So as I'm drawing from high, oops, my pen is not on apparently. So as I draw from high to low, I have to remember to curve to the right. So in the driver's seat of this wind, so if this was an airplane flying in this direction, from the pilot's perspective, we're traveling from high to low, curving to the right. So let's move up to the 30 to 60 degrees north, and still wind blows from high to low. But with the Coriolis effect, we have to bring in that rightward curve. And finally, we're starting to get somewhere. So now between 0 and 30 north, I do have a east to west directionality, and from 30 to 60 degrees north, I have a west to east directionality. So that's awesome. Let's see if it works in the southern hemisphere. So still winds blow from high to low, but in the southern hemisphere, they curve to the left as they do so. So from high to low, curving to the left, and then from high to low, curving to the left. And it gets a little tricky. You got to put yourself in the pilot seat, so to speak, to see that this is a left curve. So as you're flying this plane, looking out of the windshield, you're curving to the left. And that corresponds with our west-east movement down there in the southern mid-latitudes. So success, we've finally made it. We have a model now that explains the directionality of those global storms. Okay, so your job on the second page of your packet is to draw on this map let's see, what's the question? Indicate storm direction in the Philippines, which has the blue star on it here, and then indicate storm directions where we live. So we are up here in the northeast of the US. Okay.